In stats, we took chapter 2 a little further and we introduced the normal distribution. All right, first off, before we talk about the normal curve, a density curve, that's the curving line that you can sketch over any distribution. So if I have a skewed distribution, if I have a flat distribution, if I have a multimodal distribution, if you look at my picture here, if I draw a red line over the top of the distribution, I could get anything that looks like this or maybe even more crazy, and all of those red lines are called density curves. We call it a density curve for the portion that's above the horizontal axis, and if the entire area under the entire distribution is 100%, that means the area under the curve is 1.0. So this is the area under the entire distribution which should be 100% or 1.0. All right, so if we have a density curve that looks like the one you see at the bottom of the screen here, or maybe if I draw a smooth line over some other weird shaped graph and it looks like this, it looks positive skewed or left skewed, or uniform in the bottom right, a flat one, those are all density curves. And the area under the entire distribution, so from here to here, if I was to calculate that area somehow, geometrically or with calculus, I would get 1.0. All right? This bottom right one is really nice. It makes a rectangle. If I shade that rectangle, the area of that is 1.0. All right? We primarily focus on the normal curve right here. But every once in a while, we see a uniform one. Or maybe we'll get a sample that looks skewed like one of these two here. Who knows? But we tend to focus on the normal curve. For this opening problem right here, this is test data for students in Indiana. For some odd reason, they took an Iowa test. I don't know why. It's kind of weird. I found this in the book. Since that looks bell-shaped and symmetric, we would call it the normal curve, and we know that the mean is about the same as the median. All right? So the main idea here I wanted everyone to get is that a density curve is these two things. A density curve is a line, is a distribution above the horizontal axis, above the x-axis, and if I was to somehow calculate the area under the entire curve, I would get 1. All right? All right, let's take this further, and let's talk about normal distributions. That first curve we looked at is called the normal curve because it is normal or bell-shaped. It is symmetric, and it has one peak. All right? Now that's why we called that one on the very front of this thing normal, because it has one peak, it's symmetric. Another word we could use is mound-shaped. Symmetric doesn't quite describe it, because we could get a curve, a distribution that has all kinds of peaks in it, but yet it's still symmetric if I fold it over the middle. So be careful with just the word symmetric. That doesn't quite tell the whole story. So if it looks like that, we're going to call it normal. You can call it bell-shaped if you want, but the normal curve, we're about to look at the characteristics of it, is a very specific word, the normal curve. So many times when we take a sample, I'm going to ask, is it normally distributed? When we describe something as normal, if I notice that it's normal, I am going to first of all say it's normal. Then next I will state what the mean is. And next I will state what the standard deviation is. That gets a little tricky in terms of standard deviation because it could be a sample, and we'll talk about that down the road. But you are allowed to use just a capital N, parenthesis, and then write the mean. Or let's write it like this, sorry. All right. So feel free to write it like that, and that's the abbreviation for describing the distribution. Notice we're cussing when we do this. We're saying the shape, we're saying the center, and we're saying the spread. And for a normal curve, there is nothing unusual. There are no outliers, no gaps. All right, moving on. Let's look at that specific test data. You guys all, I hope, agree that it's bell-shaped. It has this mean, and it has this standard deviation. So we want to draw this thing in terms of the bell curve and standard deviations. So what you do is you draw a bell curve. Let me start over. And down the middle, we have our mean. So in this case, 6.84. And then we need to label the standard deviations. So we're going to need a calculator for this. We want to label 3 to the right and 3 to the left. Because most normal distributions have at least 3 standard deviations to the right and to the left. You could argue that there's 4, but it gets pretty insignificant out there when you go that far on the normal curve. So I'm going to use a calculator, and for this spot right here, 1 standard deviation above, I'm going to type in my calculator 6.84 plus 1.55. All right. I get 8.39, and then I want to go 2 standard deviations, and then I want to go 3. So on my calculator, I just keep adding 1.55, and I get these numbers. So that's 3 standard deviations below. Let's go 3 standard deviations, above. Now let's go 3 standard deviations below. And this time I'm going to start with 6.84, and I'm going to subtract 1.55. So for the first one below, 1 standard deviation below, I get 529. Then I get 374 and 219. You might try that out on your calculator just to make sure you're familiar with what we're talking about. All right, now that I know that this is the big moment here, where this is like why we take AP Stats right here. We see that the test data follows this normal pattern right here. Like, all these kids took this test, and the shape of the graph looks like this, and scores are roughly on that number line right there. This is all an approximation. This is It's not precise, but it's an approximation. So one thing we can do is we can convert that thing, all those test scores, to z-scores. So here's our curve that we just made. And in a minute, we're going to apply this thing called the empirical rule to that data. And I know that within let's write a better sigma. Within one standard deviation, we have approximately 68% of our data set. That's the one standard deviation rule. Within 2 standard deviations, we have approximately 95%, and within 3 standard deviations, we have approximately 99.7% of our data. So maybe write that on the side. Within 1 standard deviation, approximately 68%. Within 2 standard deviations, approximately 95%. And within 3, approximately 99.7. All right. I think that's enough for now. We'll take this further tomorrow. See you later.